Okay, let's dive right into this explainer and demystify one of the most fundamental frustrations in solar engineering. We're talking about that undeniable, sometimes infuriating gap between a solar module's pristine, lab-rated power and its gritty, real-world performance. You know the drill. You buy a 100-watt panel, you put it out in the sun, and you absolutely do not get 100 watts out of it. So why does that happen? Well, today, we're going to track a single photon's physical journey, literally from the sky all the way to the grid connection, and see if we can identify exactly where our precious energy is leaking away.
We're going to structure our explainer around this map, following the sunlight kind of like water in a leaky bucket. First, we'll look at the performance ratio gap. Then, sunlight's first obstacles. Third, we'll go inside the solar module itself. Fourth, the journey to the grid. And finally, designing better PV systems.
All right, let's kick things off with Section 1, the performance ratio gap, and why 100 watts doesn't equal 100 watts.
When you're designing a PV system, you just have to account for the physical reality that it will never, ever capture 100% of its potential energy. Real-world system performance typically lands at a performance ratio somewhere between 0.82 and 0.86. That means right off the bat, before we even get into the nitty-gritty specifics, there is a mystery of 14 to 18% of potential energy that is completely lost. So let's see if we can account for every single one of those missing percentage points together.
Interestingly enough, we actually have standard recommendations that show us exactly where every single one of those missing percentage points drips out of the system. And this isn't just theoretical guesswork. These standard losses are drawn from actual utility and rooftop PV systems in places like India and regions with similar climates. They represent hard-won, field-tested experience that's meant to give us highly realistic energy yield predictions. Let's zoom in and look at the actual gauntlet our photon has to run.
Moving right along to Section 2, sunlight's first obstacles, specifically the atmospheric and surface hurdles.
Let's start with the hurdles our brave little photon faces before it even manages to penetrate the solar cell glass. Sunlight immediately loses a recommended 2.5% to soiling, and yep, that means dust, dirt, and bird droppings. Then, because the sun is constantly moving, 2.0% is lost to the incidence angle modifier. Basically, light striking at bad angles simply bounces right off. Add in 1.0% for near and far shading from things like buildings or trees, and another 1.0% spectral loss, because the atmospheric solar spectrum just doesn't perfectly match what the module is designed to absorb. Before the photon even touches the silicon, we are already down roughly 6.5%. No way, right?
Next up is Section 3, inside the solar module, where we look at the intrinsic hurdles.
So the photon has finally made it inside the silicon. Success. But the physical reality of the module itself creates the next big leaks in our bucket. The absolute crucial point here is understanding temperature loss. Solar panels are rated at standard test conditions, which is a cool, comfortable 25 degrees Celsius. But in reality, they sit outside just baking in the sun. This temperature loss penalizes the system anytime the module gets hotter than its pristine lab conditions, and it is highly dependent on your site-specific climate.
And listen to this. This thermal penalty is the absolute biggest energy drain in the entire gauntlet. It costs a massive, roughly 8% in recommended standard value. Let that sink in for a second. Just the sheer fact that panels get hot in the sun eats up 8% of your potential energy. If you only remember one single number from this entire explainer, make it this one.
The module isn't done taking its cut. Inside, you lose a collective 6% almost immediately. There's a 2.0% module quality loss just from basic manufacturing tolerances. Panels just don't perfectly match their datasheets, it's a fact of life. Then you've got a 2.0% mismatch loss because panels in a string have slightly non-uniform characteristics, essentially dragging each other down. Add another 2.0% for light-induced degradation, which is that initial performance shock when panels first hit real sunlight. And of course, we can't forget the unavoidable 0.5% structural degradation every single year as the physical materials age.
Which brings us to Section 4, the journey to the grid, otherwise known as the electrical escape route.
Okay, our photon has now been successfully converted into direct current, DC power. But it is definitely not home free. The physical journey to the grid connection point extracts its own toll. First, the current faces a 1.0% resistive loss just pushing through the DC cables between the modules and the inverter. Then, it squeezes past blocking or bypass diodes, costing a minor but fixed 0.2-volt drop. Finally, hitting the AC wiring, there's another 1.0% loss just battling line resistance before it even gets to the transformer. Keep in mind, the physical length and thickness of your cables directly dictate how big these leaks are. Now, when we compare these electrical losses side by side, a really interesting picture emerges. While proper string design keeps voltage variations to a tiny, almost negligible 0.10% drip on the MPPT input, pumping that power through a step-up transformer and a medium voltage line guarantees a much larger 1.0% drop. You can design the most perfectly matched DC strings in the world, but the heavy lifting of actually stepping up the voltage for the grid is always going to demand a heavy toll.
Finally, we have to deal with the operational realities of actually running a power plant. System auxiliaries. We're talking about things like tracker motors physically turning the panels, monitoring devices, SCADA systems. They consume 0.5% of the power themselves. Then you have availability loss. Planned maintenance downtime or grid outages will cost you another 0.5%. And because the physical world is just messy, miscellaneous, unquantified electrical losses drain a final 0.2%. And just like that, our bucket is officially empty of those 14 to 18% of lost watts.
Let's wrap things up with Section 5, Designing Better PV Systems. It's time to put all this data into practice. Knowing exactly where the energy drips out of the bucket is really only half the battle. The actual key is putting this data to work. Think about the scale of these numbers. That uncontrollable temperature loss is a massive 8% penalty. You can't change the ambient weather, but controllable elements, like scheduling regular cleaning to stop those 2.5% soiling losses, heavily outweigh sweating over a minute 0.1% electrical mismatch. You can't easily cool down the sun, but you can definitely schedule a panel washing truck, right? It's all about focusing on the biggest levers you can actually pull. This is exactly why standard practice guidelines remind us not to just blindly use default software numbers forever. The best models out there ground truths these recommendations. That means verifying your assumptions using site-specific soiling studies and actual O&M records. You need to cross-verify those 1.0% transformer losses using real electrical design calculations in software like STAT or ETAP. Adjust your auxiliary loss assumptions based on actual plant operation logs from similar sites. And crucially, please don't forget this. Always remember to turn on that 0.5% degradation parameter in PVsyst for long-term simulations. So now that you've tracked the photon's incredibly hazardous journey from the sky all the way to the grid, you understand exactly why a 100-watt panel doesn't yield 100 watts of usable power. The physical world extracts its tolls through heat, dirt, resistance, and mechanical necessity. So, armed with this map of the exact leaks in the system, how will you use these benchmarks to build a better model and squeeze every possible drop of power out of your next PV system? Remember, it's all about designing smarter, not just bigger.